Weighted least squares. First, we're going to get the weighted least squares data set, which was tailor-made by SPSS for this. We go to data, and you're going to see WLS dataset.save. And just open it up. It's an SPSS file, and here you can see the two variables. You're going to see education in years as the independent variable, and the dependent variable will be salary that results from the education. So ordinary least squares assumes that all observations have the same variance, but often this is not the case. The solution is to weigh the cases by the reciprocal of their variances, which is 1 divided by their variance. This is the effect of reducing the impact of observations with large variances and having less of an effect on observations with a smaller variance. So how do we diagnose the relationship? Well, we would plot the residual y-axis and the predicted x-axis, and we would see if they're not randomly distributed in the scatter plot, especially if they form a funnel in any cardinal direction or a bow tie. And we could look from the zero of the residual for symmetry. If we don't have this, then in this case the variances are unequal. This is what we see when we see heteroscedasticity, when the standard deviation of the residuals are uneven. And we also see this when we see first order autocorrelation, called serial correlation. But we'll talk about that later when we see time series. And time series autocorrelation has its own solution to deal with that problem. So what are we going to do? We're going to run a linear regression. So here we've got a theory of years of education that correlates with final career salary. So let's run the procedure here. So we're going to go to graph. We're going to go to legacy dialogues, to scatter plot, and we're going to go to simple, define, and we're going to put into the y-axis the salary and the education level, which is the independent variable, into the x-axis, and we're going to see what it looks like. So here you see on the left it's pretty compact, but as we're going to the right it gets more and more diffuse and spread out. So here we have heteroscedasticity, and weighted least squares is going to help solve that problem. Let's take a look at the regression. We go to Analyze, Regression, Linear. Into Dependent, we're going to put the salary. Into the Independent, we're going to put education. And then we're going to go and we're going to save the predicted standardized and unstandardized, and the residual standardized and studentized. And we're going to click continue and then go to plots, and in plots we're going to put into the y coordinate z resid, or the standardized residual, and into the x axis we're going to put the standardized predicted. Alright, then we click continue and we run the regression, and we're going to see that the r squared, adjusted r squared, but here the r squared is fine because we have it's bivariate, is 0.436, so we have a moderate association. We can see in the f statistic that it's fully significant, the entire model. We can see here that in the t statistic the independent variable is fully significant as well. We keep coming down here, and we see on the scatter plot, like we saw before, a leftward funnel, which indicates an increase in variance across the values of the scatter plot. So here we have a diagnosis. If heteroscedasticity is detected in a model, the bivariate IVDV regressions are to be run to isolate which bivariate model produces the heteroscedasticity. If the heteroscedasticity is the result of a combination of independent variables, and the independent variable from the most heteroscedastic bivariate relationship is to be used as the weight. Here it's bivariate, so we can imagine that if we had a multivariate model, we would have worked through it and had eventually identified this as the independent variable causing the heteroscedasticity. So what are the benefits of weighted least squares? It improves and provides more accurate standard errors of the B coefficient, which is the standard deviation of the slope. It improves, consequently, the statistical inference. So it'll improve the t-statistic. Weighted least squares will not function if you have any omitted variable bias. So if you're missing a variable and you don't include it, weighted least squares is not going to improve the heteroscedasticity to homoscedasticity. You have to actually include any variables that are missing. Okay, so let's start the procedure. So there are several steps, and in step 1 we're going to go to Analyze, Regression, and we're going to go to Weight Estimation. And in Weight Estimation, I'm going to widen this out so we can see better. We're going to put salary into the dependent variable. We're going to put education into the independent variable. And we're going to input into the weight variable education. Right? Because education is the independent variable. And in options, we are going to save the best weight as a new variable. Okay, and we're going to click OK and run this. So we have here a power summary. And so a quick discussion about power ranges. The power ranges indicate the power values to be used in computing the weights, and should fall typically within -6.5 to 7.5. The weight variable is the value W, where in the formula you have 1 over W, and it's to the power of power. So the variable will be saved as WGT_n, where n is a number. So let's see what we have here. Here we go. Here's WGT_1, and it indeed has been saved. The n value means how many times you run it. If you run any of these values here more than once, you'll have a second version, a third version, a fourth version, and that number will increase at each step. So now we go to step 2. In step 2, we go to Analyze, Regression, Linear. Again, we have salary as the dependent variable. We have education as the independent variable. We've saved the predicted standardized and unstandardized. In the residuals, we've saved the studentized and the standardized. And we input into the WLS weight. We insert into it WGT1. And then we click OK. So now, in theory, we have a more accurate model. Here we've got an R² of 0.354. We still have a good F significance. Our T significance is still very good. So now we want to verify this. When ordinary least squares regression is run with the WLS weight variable, we would save the predicted and the residuals. These must both be transformed by multiplying them by the square root of the weight variable before they are plotted. And the plot should show no funnel shape. So it should reduce the funnel shape we saw before. So we've done this before. We're going to go to Transform. We're going to go to Compute Variable. And here we're going to insert as the target value WRes. All right. And we're going to insert arithmetically the square root. All right, so we put the square root up here, and we're going to widen this out so we can read it. And we're going to insert WGT1. To insert, there we go. And we're going to insert that into the square root. And we're going to insert the expression ZRE, standardized residual, and times ZRE. And we're going to click OK. So it should add a new variable, which in fact it has. Well, I have here the WRes. And now we're going to make another transformation. We go back to Compute Variable. This time we're going to put a target value W pred. Again, we've got square root WGT1, and this time we're going to have it multiplied against ZPR1, which is the standardized predicted value. So here we have ZPR1. We click OK. We'll have a new variable added. We in fact do, WPRED. So what we did was we computed WRes is equal to square root of the weighted value times the standardized residual, and WPRED was the square root of the weighted value times the standardized predicted value. Or we could have used the studentized values. So the final step is to confirm that we've gotten rid of the funnel. So we can plot WRes against WPRED and see what the improvement is. So we go to Graphs, Legacy, Scatter Dot. We're going to go for Simple, Define. We're going to put WRes into the y-axis, WPRED into the x-axis, and let's see what we have. And we have a diminished funnel. If we look at the previous, here much more diffuse on the right, here much less diffuse. But nevertheless, you have some diffusion. So this is weighted least squares.